Okay, so welcome to the fourth TA session uh, of this course, Signals and Systems, Principles of Signals and Systems, offered by Professor Aditya Jagannathan from IIT Kanpur. Um, my name is Yashvanth, and I'm a PMRF PhD student at in the Department of EC at IISc Bangalore. I'm advised by Professor Chandramurthy, and my broad research interests lie in signal processing and applications to wireless communication systems. So, my current focus is on designing intelligent reflecting surfaces for 5G and beyond wireless technologies. Course contents and in particular of the problems that we solve in the in the TA sessions, live interactive sessions, you can feel free to mail me in this email, and you can know more about me, my interests and everything in this web link given here. That's like a very short brief introduction about me. So the topics covered for week 4 include Laplace transforms, properties of Laplace transforms, characterizations of systems using Laplace transform. Okay, so in the last TA session, we had solved quite a number of questions on how to perform convolution of any two signals using the definition and also using graphical methods. So that was about convolutions. And this week, all the questions that we'll be solving will be on Laplace transforms. Okay. So first part of this today's class will, as usual, be to quickly summarize the contents of week 4's lectures. So, so quickly recall that the Laplace transform of a signal x of t is given by this equation, that x of s equals integral minus infinity to plus infinity x of t e power minus st dt. Okay, so the way to think about a Laplace transform, what does it physically do? Basically represents a given signal x of t in the Laplace domain. If I write that signal x of t, that means essentially this is a signal value at time t. That means x of t is in time, it's a time domain signal. But x of s, which is computed by this integral, is also the same signal but in the Laplace domain, where s is the Laplacian variable s. Like how x of t is a time domain signal indexed by time t, x of s is also the representation of the same signal but in the Laplace domain. That's why it's called a Laplace transform. Okay, s is the Laplace variable. Now the properties. Okay, so I pulled out a small table. This reference for this table is Oppenheim Signals and Systems. So this is table number 9.1 in the book. So I wanted to quickly go through what are the properties of Laplace transform. Okay, so but chapter number 9 deals with Laplace transforms, and this book by Oppenheim, and these are different sections in the book covers each of these properties in detail. And second column is on property, and third column says what property of the signal mathematically, what how is the property captured by the signal. The fourth will tell, okay, for this property how does a Laplace transform behave, and finally the ROC. Remember, recall that a Laplace transform always is accompanied by two things. One is this integral value, the other is the region of convergence or ROC. We should specify both in order to uniquely characterize the Laplace transform of any signal x of t. All right, so let's quickly go over the different properties of Laplace transform, which is also covered in the class. Okay, so consider that we will consider different notions. Let's say x of t will have the Laplace transform capital X of s, x1 of t will have the Laplace transform x1 of s, x2 of t will have the Laplace transform x2 of s, and corresponding region of convergence is R, R1, R2. Okay, the first property is a linearity property. Namely that if the Laplace transform of x1 of t is x1 of s and x2 of t is x2 of s, then a times x1 of t plus b times x2 of t, the Laplace transform of this a x1 of t plus b x2 of t is nothing but a x1 of s plus b x2 of s. That is basically the linearity property. Okay, that is what it says is just replace x1 of t by its Laplace transform x1 of s and x2 of t by its Laplace transform x2 of s, multiply by a and b, and then add both of them. That will be the Laplace transform of the ax1 plus bx2 of t. This is called the linearity property of Laplace transform. Now, what will be the ROC? ROC will be at least the ROC of x1 of t intersection the ROC of x2 of t. Okay, the second property, the time shifting property, what it says is, suppose if you have the Laplace transform of x of t as x of s, then a time shifted version of the signal x of t minus t naught will have the Laplace transform e power minus s t naught times x of s. Okay, essentially this minus t naught will come in the as an additional exponential multiplication term, but we're having the Laplace variable also e power minus s t naught, where t naught is the amount of time delay that you apply to the actual signal x of t. But how will be the ROC? ROC will not change. That is, the ROC of x of s will be the same as the ROC of x of the Laplace transform of x of t will be the same as the ROC of the Laplace transform of x of t minus t naught. The third is called the shifting in the S domain. That is the Laplace domain. Suppose if the Laplace transform of x of t is x of s, then the Laplace transform of e power s naught t times x of t is x of s minus s naught. Okay. Now the corresponding ROC will be the shifted version of the R. Okay, that is basically, if let's say this is ROC, then you basically shift it by amount s naught. Okay, basically you just move the entire set in the S domain. That is the ROC of shifting in the S domain. Now you see how this is like a dual nature. When you do a time shifting, you get exponential multiplication in the Laplace domain. Similarly, when you do an exponential multiplication in the time domain, you get a Laplace domain shifting. That is S domain shifting. So this is like the dual property that you observe between the time domain and the Laplace domain. Next property is time scaling. If the signal x of t has the Laplace transform x of s, then x of at will have the Laplace transform 1 by mod a times x of s by a. What will be the ROC? The ROC will be the scaled version of the ROC of R. So R, let's say, was ROC. Now you will have the scaled version of R as the ROC for the Laplace transform of x of at. Now conjugation. So if x of t has a Laplace transform capital X of s, then x conjugate of t will have the Laplace transform x conjugate of s conjugate. That is, you will conjugate the function and also the variable of the function s. And the ROC will not change. That is, it remains this R. Now, convolution, there is a very important property. We will use this very often when we go to characterizing the systems using Laplace transform. Very important property. Convolution property of the Laplace transform says that if x1 of t has a Laplace transform x1 of s and x2 of t has a Laplace transform x2 of s, then the Laplace transform of x1 of t convolution x2 of t is the product of the Laplace transform. That is, the convolution will now become product in the Laplace domain. Very important property, which we will use to simplify the solution. It's a short trick. Instead of convolution, all you can do is go take the Laplace transform and do the multiplication, and then take the inverse Laplace transform. Okay, so we will use such kind of tricks in our using this property for systems, analyzing systems. And if it's a product of the Laplace transform, and the ROC is an intersection of the ROC of x1 and ROC of x2. Differentiation in time domain. If x of t has a Laplace transform x of s, then d by dt of x of t will have the Laplace transform s times x of s, with the ROC being at least R. Similarly, okay, let me do this. Differentiation in S domain. So this was differentiation in time domain. Now this differentiation is S domain. That is, if x of t has a Laplace transform x of s, then minus t times x of t will have the Laplace transform d by ds of x of s. The Laplace and the ROC is unchanged. You see, again, there is some kind of a dual property. If you differentiate in one domain, in the other domain you have s times x of s. Similarly, if you differentiate in the Laplace domain, in the time domain you have t times x of t, except that there's additional negative sign. So the variable gets multiplied in the other domain compared to the differential, where you take the differentiation in the other domain of the domain in which you take the differentiation. Finally, integration in time domain. This property says that if x of t has a Laplace transform x of s, then integral minus infinity to t x of tau d tau will have the Laplace transform 1 by s times x of s. Here, the ROC of the Laplace transform will be r in intersection the plane covered by the positive values of x. That is, real part of s is greater than 0. That means what? This is s is equal to, what is s? S is nothing but sigma plus j omega. If real part of s is greater than 0, that means what? Sigma is greater than 0. So everything to the right hand side of the j omega axis is the what? Is the region covered by this second set. This is a set of all points in the right side of j omega axis is what is characterized by real part of s greater than 0. Now take intersection of that set with the actual ROC of x of t. That will be the ROC of this signal, Laplace transform of this signal in minus infinity to t x of tau deta. Okay, so these are the very commonly used properties. Which, if you keep practicing problems on Laplace transform, with time you will automatically remember all the properties. It is not very difficult. Okay, it's only 9 properties. If you keep practicing, you will automatically memorize these properties. It's very easy. For example, you see that these are like dual properties. If you remember one, the other one you can make out. Okay, there are also something called initial and final value theorem, which we will take it up maybe towards to later in the course, but we will not discuss them now. Okay, these are very again useful theorems in Laplace transforms, which will help us to determine the characterizations of systems. For example, how well is a system stabilized? Right? What will be the what will be the stationary output of a system? For those kind of problems, we make use of something called initial and final value theorem. But for now, we will skip it. We'll take it up later in the course. Okay. Now that was about Laplace transform and properties. Now, what are some of the Laplace transform of some elementary functions? That is, some functions which it is always good to remember the Laplace transform of very standardly occurring signals, so that we will be using them at many points in time. Okay. So the first signal is delta of t. There is an impulse function. What is the Laplace transform of an impulse function? It is nothing but equal to 1. That is, x of s is equal to 1. And what is the ROC for all s? That is in the entire s plane. Right? This is your s plane. This is j omega axis. This is your sigma axis. The entire s plane, ROC, the Laplace transform exists, and its value is equal to 1. Okay. Now u of t, that is a unit step function. The Laplace transform u of t is 1 by s. It is x of s is equal to 1 by s, and the ROC is real part of s greater than 0. That is towards the right hand side of j omega axis. Is the ROC where this Laplace transform of 1 by s exists. Now take u of t is this. Similarly, it turns out that minus u of minus t. What is minus u of minus t? So basically, minus u of minus t is basically equal to minus 1 in the negative t domain. Okay, for negative t domain, you have minus 1, else it is 0. This is basically minus u of minus t. Okay, so this is a very different signal compared to u of t. U of t is equal to 1 for positive t axis, but for negative axis it is 0. But minus u of minus t, it takes a value minus 1 in negative t axis and takes 0 value in the positive t axis. So both signals are different, but you see both the Laplace transform turn out to be the same, 1 by s and 1 by s. So then you can ask, okay, so where is the difference? Difference is in ROC. Exactly the opposite ROCs. That is, real part of s, if it is greater than 0, then u of t will have a Laplace transform 1 by s. If the real part of s is less than 0, then 1 by s corresponds to Laplace transform of minus u of minus t. Okay, that's why I told always ROC is very important. If someone asks you what is the signal for which Laplace transform is 1 by s, I cannot uniquely tell. If someone also gives you the ROC with it, then I can uniquely tell what is the signal for which the Laplace transform is 1 by s. Fine. The next signal is t power n minus 1 by n minus 1 factorial times u of t, whose Laplace transform is 1 by s power n, and the ROC's real part of s is greater than 0. Similarly, if you have minus t power n minus 1 by n minus 1 factorial u of minus t, then the Laplace transform is 1 by s power n, and real part of s is less than 0. Same thing. You see 1 by s power n is appearing for both two different signals as the same value, but the difference comes in their ROCs. Similarly, if you take e power minus alpha u of t, sorry, e power minus alpha t u of t, the Laplace transform is 1 by s plus alpha, and the ROC is real part of s is greater than minus alpha. But on the other hand, if you take the signal minus e power minus alpha t into u of minus t, that also has the same Laplace transform 1 by s plus alpha, but with a different ROC. Namely, real part of s is less than minus alpha. Here it was greater than minus alpha, here it is less than minus alpha. Similarly, now combine this 4 and 6. That is equation 8. Okay, basically what it says, you combine 1 by s power n and 1 by s plus alpha, that becomes 1 by s plus alpha whole power n. Okay, so you can, how to do this? Just use properties. What did we do? We just multiplied by e power minus alpha. So what will happen? There will be a shift in the s domain. Why? Go back to the properties. Whenever you multiply by e power s naught t, you will have a shift in the Laplace domain. Exactly that's what happened here. You see, e power minus alpha t, you have shifted by a value of alpha. So your Laplace domain. So early we had only u of t, whose Laplace transform is 1 by s. But now you have multiplied with e power minus alpha t. So the Laplace in the Laplace transform of u of t, s will be shifted by an amount of alpha. That's why it is 1 by s plus alpha. Just by using the properties of the Laplace transform, you can make out. That is one way, or you go with the definition of Laplace transform, evaluate the integral, and you can show it is 1 by s plus alpha. So by using the same logic, if you just consider that your signal, okay, let me just write down. If let's say your x of t is equal to t power n minus 1 by n minus 1 factorial into u of t, which is basically your port signal. It is x of s is nothing but 1 by s power n. Now, if you multiply x of t with e power minus alpha t, then what will be the Laplace transform? X of s plus a. S will be replaced by s plus a. So 1 by s power n will become 1 by s plus a power n. And that is exactly what you see here. Why x of t into e power minus at will become x of s plus ia? By this property. I just used this property here. Here s naught is minus a. That's why it becomes x of s plus s naught. S plus a. By just using the property of the Laplace transform. Okay, and that's how you can get this 8. Similarly, you get 9. Okay, so and you can find delta function. Delta of t minus t naught is nothing but e power minus st. Similarly, you can derive for cos omega naught t into u of t, sine omega naught into u of t, e power minus alpha t into cos omega naught times u of t. Now you see that again I'm multiplying e power minus alpha t times cos omega naught u of t. But I know the cos omega naught u of t already has a Laplace transform s over s square plus omega naught square. So if you multiply by e power minus alpha t, s will be replaced by s plus alpha. That's why you get s plus alpha divided by s plus alpha whole square plus omega naught square. So just by using properties of the Laplace transform, you can obtain one from another. Similarly for e power minus alpha t also. Now un of t is, let's say, defined as the nth derivative of delta of t. Now this will have the Laplace transform s power n. Again you can make use. You see, go back to this differentiation. Okay, this guy, right? So what it says, d by dt of x of t will have the Laplace transform s times x of s. Now delta of t, see, look at this table. Delta of t has a Laplace transform of 1. Therefore, if I differentiate the delta of t n times, I have to multiply s n times, because you see delta of t has a Laplace transform 1, and as per this property, if I differentiate once, I'll multiply by 1s. X of s is anyways 1 for if x of t is delta of t. Right. So basically by differentiating 1 times, I will get just s. If I differentiate 2 times, I'll get s into s, which is s square. Differentiate 3 times, s cube. So if I differentiate n times, I get s power n. That is, so you can basically obtain again this by using the Laplace transform of delta of t and by using this property. differentiation and the time domain property of the Laplace transform. Similarly, you can show that if you convolve u of t n times, then the Laplace transform will be 1 by s power n. Why? U of t has a Laplace transform 1 by s. You see here, u of t has a Laplace transform 1 by s. But I told that convolution in time domain is same as multiplication in the Laplace domain. So if u of t has Laplace transform 1 by s, convolving u of t n times is same as taking product of 1 by s n times, which is 1 by s power n. Okay. Okay, so this is basically properties and some standard signals. Again, as you keep practicing some problems, it is easy to memorize at least some of these Laplace transforms. It is, in fact, I would suggest that it's good to memorize most of it. In fact, for example, you need not memorize 8 and 9. If you know just 4 and the properties of Laplace transform, you can derive 8 and 9 by just using properties of Laplace transform. So you don't need to memorize everything. Just memorize some basic things and use the properties of Laplace transform to derive the others. Okay, now the concept of poles and zeros. So let's say the Laplace transform is expressed as a fraction, okay, where the numerator is some function of Laplace domain S, Laplacian variable S, and the denominator is some other function in the Laplace domain, Laplace variable S. Now let's say the numerator is a polynomial in S with degree m, and denominator is another polynomial in S with degree n. Okay, then the poles or is the zeros of this Laplace transform is defined as set of all the Laplace domain variable S wherever the numerator goes to 0. Okay, this set is called the set of all zeros of the Laplace transform X of S. Similarly, if I collect all those values of the Laplacian variable S for such that the denominator at these values goes to 0, then this set is the set of all poles of the Laplace transform X of S. Okay, if your m, that is the degree of numerator, is greater than n, then it's called an improper Laplace transform or improper fraction. If your degree of numerator is less than degree of denominator, then it's called a proper Laplace transform or proper fraction. Now let's take an example. If I say x of s is equal to 2s minus 3 by s plus 1. What is the numerator? Numerator polynomial is 2s minus 3 and denominator polynomial is s plus 1. Therefore, wherever you equate n of s is equal to 0, what is s? S is nothing but 3 by 2. So this Laplace transform x of s has only one 0 and that occurs at s is equal to 3 by 2. Similarly, the denominator polynomial is s plus 1. If you equate this to 0, I get s is equal to minus 1. That means this Laplace transform has only one pole that occurs at s is equal to minus 1. Fine. Now, some properties of the Laplace properties of the Laplace transform that are related to the poles and zeros of the Laplace transform. Poles cannot be in ROC. That is, see, s is equal to minus 1 will not lie in the ROC of the Laplace transform X of s. That's a property. Why? Because at poles are the values at which the denominator goes to 0 or X of s goes to infinity. But ROC by definition is a set of all s for which it's a finite number. That's why ROC can never contain pole. Poles of any Laplace transform will not lie in the region of convergence of the Laplace transform. For a finite duration signal, the ROC is the entire S-plane. So for what you may finite duration, this is an example as I show here. That is, it takes a value, a non-zero value only for some finite value of time. Everywhere else it is 0. So it's a finite duration signal. Only for some finite amount of time, the signal takes a non-zero value. So this is called a finite duration signal. And it turns out that for any such finite duration signal, the ROC of its Laplace transform will be the entire S domain plane. For a right-sided signal, the ROC will also be a right-sided plane. That is, what I mean by right-sided signal is, if you draw the time domain signal, it is only having non-zero value in the right side. Okay, I'm not saying with respect to 0. No, it could also be like this. So for example, it could also start here and goes. For example, this is minus 2, let's say. This is also a right-sided signal. All it says is there should exist some left, some t tending to minus infinity where the signal is 0, takes a value 0. That is, the signal only should be a right-sided signal, not a left-sided signal. For a right-sided signal, whatever be the signal, but if it's a right-sided signal, then the ROC will be of the form real part of S is greater than sigma max. where sigma max is the real part of the maximum value of the pole of the Laplace transform x of s. That is, if I draw the s domain, j omega axis and sigma axis, take sigma max, and everything to the right of sigma max is the ROC. Similarly, for a left-sided signal, for example, you see this is a left-sided signal. After t equals 0, it goes to 0. This is a So basically, this is a left-sided signal. Okay, it has all non-zero values towards t tending to minus infinity, but at some point of tending towards t equal to infinity, it becomes 0. Here at t equal to 0, the x of t also becomes 0. This is a it's called a left-sided signal. That is in time domain, it's a left tail signal or left-handed signal. It's not a right-handed signal. For a left-sided signal, the ROC of this Laplace transform will take the form R of s is less than sigma min, where sigma min is a real part of the minimum pole. As an example, again, if I take the imagine the j omega axis with a sigma plane, let's say mark sigma min here. Everything to the left of sigma min will be the ROC. Now, finally, the two-sided signal, that is, it takes non-zero values in both negative and positive t axis. The ROC will be a finite strip. See here, that is, for a right-sided signal, the ROC is also right-sided. For a left-sided signal, the ROC is also left-sided. But for a two-sided signal, the ROC is a finite strip between sigma min and sigma max. Okay, it's a finite strip on the sigma axis, but it can extend in y axis. It can extend anywhere, but in terms of x axis, it's a finite strip. Okay. So these are like the four. First, we started with the finite duration signal, which is neither left or not right, because as t tends to infinity, the signal value goes 0. Similarly, at t tends to minus infinity, or signal value goes to 0. So it is neither left or nor right side signal, for which the ROC is the entire S plane. But for a right sided signal, the ROC is only right sided. For a left sided signal, the ROC is left sided. And for a two sided signal, the ROC is now not entire S plane. It's a complete opposite. That is, it takes only a finite strip in the entire S domain plane. Okay. Next is the partial fraction expansion of Laplace transform. So what is the usefulness of this? It is used in finding the inverse Laplace transform. Okay, this is another just a procedure that you need to know. Suppose P1, P2 and so on till Pn are distinct poles of a Laplace transform. Then you can express the Laplace transform x of s as a partial fraction, sum of partial fractions like this. C1 divided by s minus P1 plus C2 divided by s minus P2 and so on to that is, the values of the c's is given by s minus pk times x of s evaluated at s is equal to pk. This is if all these this is correct if all these poles are distinct poles. Now, if there are multiple poles, that is, some given pole is repeating n times or r times, then how will the partial fraction be looking like? What you need to do is you need to that the pole which repeats r times, you need to represent the term for that pole using r terms. Okay, and how? So let's say pi repeats r times, then the term corresponding to pi in the partial fraction expansion of x of s should have r terms, namely lambda 1 by s minus p1 plus lambda 2 by s minus p1 whole square and so on to lambda r divided by s minus pi whole power r. And how to find these lambda values? It is given by this expression here. Lambda r minus k equal to 1 by k factorial d power k by ds power k as the kth derivative of s minus pi power r into x of s evaluated at s is equal to pi. I think this is very similar to all those who have done engineering mathematics. You will have to do something called complex integration. Whenever you and if you recall, there is whenever you want to do an integration with respect to complex valued variable function, what you do, you compute something called residues. It's a residue value theorem, right? This is exactly the value residue that you're computing here. Okay, so basically it's a why are we reusing that here? Essentially because s is what? S is a complex variable, and if Laplace transform is defined as integral, inverse Laplace transform is also defined as an integral, and basically you're integrating a complex valued function x of s. X of s is a complex, see, it's a x of s is a complex valued function. S is a complex variable. So you're integrating x of s in order to get x of t, inverse Laplace transform. Inverse means you're given x of s and you want to get x of t. Means you need to integrate over x of s, a complex valued integration. And essentially this is nothing but going by residue procedure. You're doing a complex integration. That's where you go with this pole business and partial fraction expansion, and then you do a residue theorem to get back the inverse Laplace transform. Okay, now we discuss about Laplace transform. Now, how is Laplace transform used in characterizing a system, LT system in particular? So let's say x of t is the input to an LT system whose impulse response is h of t and gives an output y of t. Then it so turns, and let's say the input signal has a Laplace transform x of s. The impulse response h of t has a Laplace transform h of s, and the output y of t has a Laplace transform h of s. Then we know that if y of t is equal to x of t convolution h of t, but using the property of Laplace transform h of basically what we get is that y of s is equal to x of s into h of s. That is, a convolution become product in the Laplace domain. That is a proper convolution property of a Laplace transform. Or in other words, okay, so this is basically y of s. I don't know. Okay, this is y of s. Yeah, same. Okay, now h of s is also called the transfer function of a system. That is, you take the Laplace transform of the impulse response, and that Laplace transform is given a special name called the transfer function of the system. Now, you remember, we characterized the causality, stability, memorylessness of an LTI system by characterizing its impulse response. Like, for example, impulse response should be right-sided in order for a system to be causal. Right? We said something like that. We characterize those systems using impulse response. Similarly, you can characterize the causality and stuff, stability and all these things using the transfer function also. Okay, so in terms of causality, recall that we told that your impulse response should take the value 0 whenever t is less than 0. That is, the impulse response should be a right-sided signal. That is needed for causality. In terms of the transfer function, in terms of the Laplace transform of the impulse response, the same condition becomes your transfer function should have a right-sided ROC. Okay, this is something that we saw above, right? That a right-sided signal will have a right-sided Laplace transform. So if your ROC is such that real part of it is greater than sigma max, then that particular h of t, that particular system is a causal system. Similarly, for stability, BIBO stability, recall that in terms of impulse response, the impulse response should be absolutely integrable. In terms of the transfer function, the ROC should contain j omega axis. If it contains, that is, the ROC should have sigma equal to 0. If sigma equal to 0 is included in the ROC, then that system is a BIBO stable system. Okay, and finally, how to find the characterizing the input-output relation of an LT system using Laplace transform. So recall that last time itself, we told that any LT system can be represented as a linear constant coefficient differential equation. That is exactly whatever is written here. Okay, now using Laplace transform, this basically what happens is that the kth derivative of y of t will become s power k. Correct? Yeah, s power k, and basically replacing that, you get this. That is, h of s is equal to y of s by x of s, which is nothing but this divided by this. And finally, the definition of one-sided Laplace transform, or it's also called unilateral Laplace transform. The main utility of this kind of Laplace transform is to analyze the output of a system which is initially at rest. That is, at t equal to 0 only, you are starting to use a system. For those kind of systems, you will basically make use of unilateral Laplace transforms. What is the main difference? For a unilateral Laplace transform, the definition is from 0 to infinity. Recall for a normal regular Laplace transform, the definition goes as minus infinity, integral minus infinity to plus infinity, x of t e power minus st dt. But now it is not from minus infinity to plus infinity, it's only from 0 to infinity. Okay, so all the properties of unilateral Laplace transform is similar to the regular Laplace transform, except for a few changes. For example, if you have d by dt of x, if x of t has unilateral Laplace, one-sided Laplace transform or unilateral Laplace transform xi of s, then the derivative of x of t will have the times xi of s minus x of 0, where this is small x. Remember, this is basically what it says is whatever is the time value, whatever is the signal value at x equal to 0, that you need to subtract. Okay, this is the extra term that you have in unilateral Laplace transform. If it were regular Laplace transform, you just have this. But if it's a unilateral, you have this minus the second term. Similarly, for the integration property also, if you take the basically if you have this property that the unilateral Laplace transform is basically of x of tau, the integration will have xi of s divided by s. And similarly, if you basically integrate from minus infinity to t, then you will basically also add the extra term that incurs apart from xi of s by s. Okay, but this is not something very important, but just to know it's okay. Unilateral Laplace transform. Fine. So that is about Laplace transforms, properties of Laplace transforms, and some of the characterization of systems using Laplace transforms and transfer function. If there are any doubts, you can ask me. Otherwise, we can start with some problems for today. Yes, if there are doubts, you can ask. Otherwise, let's begin with problems for today. Okay, so I don't see anyone asking a question. So let's then start with problems. The first question is, using the properties of Laplace transforms, find the Laplace transforms of the following signals. From the Laplace transform of u of t. Okay. The first one is delta of t. Okay. So basically what it says is, let's say you are given the Laplace transform of u of t. Okay. What we are asking here is, find the Laplace transform of delta t by making a function using the prop. So you only know the Laplace transform u of t. Using that, you need to find the Laplace transform delta of t. And how do you do that? By using the properties of Laplace transforms. This is what the question is about. So let's do it. The trick is to identify that delta of t is related to u of t by d by dt of u of t. That is, if you differentiate the unit step function, you get the unit impulse function. Okay. Now, what is the Laplace transform of u of t? Is equal to 1 by s. You go back to the table, you will see. Okay. The Laplace transform of u of t is equal to 1 by s. Therefore, if x of t has a Laplace transform, okay, x of s, what is d by dt of x of t? It will have the Laplace transform s into x of s. How? Let's go back to the table. See the table here. D by dt of x of t will have a Laplace transform x times s times x of s. So what is known to me? What is known to me is that this x of t is u of t. So 1 by x of s is 1 by s. So d by dt of x of t is delta of t. So it will have the Laplace transform s into 1 by s, which is equal to 1. Okay. Therefore, your delta of t will have the Laplace transform s into 1 by s, which is equal to 1. And this exists for all values of s. Therefore, the ROC is all values of s. Okay. Now the second question is delta dash of t. That is the differentiation of delta of t. The differentiation of delta of t is not something physically a useful quantity, but for mathematically it is still a well-defined function. Okay, so it's not something physically useful, but mathematically it's still defined. So tell me, can anyone tell me now what is the answer? How do I find the Laplace transform of t, delta dash of t? Yes. Okay. Simple. Okay. So what is delta dash of t? It's nothing but d by dt of delta of t. That is nothing but d square by dt square of u of t. Okay. Therefore, if x of t, okay, let x of t be u of t, which means x of s will be equal to 1 by s. So x of t, if it has a Laplace transform x of s, then d by dt square, d square x of t by dt square will have the Laplace transform s square into x of s. But x of s is nothing but 1 by s. Therefore, the delta of t will have the Laplace transform s square into 1 by s, which is equal to 1 by s. 1 is equal to s. Okay. Again, ROC is what? All s belonging to minus infinity to plus infinity, but open interval. I don't want infinity to be inside. Otherwise, it will not converge. Now, third question. T into u of t. How do I find the Laplace transform of t into u of t if I know the Laplace transform of u of t? Okay. Again, by property. My property is that if x of t has a Laplace transform x of s, then t into x of t will have the Laplace transform minus d by ds of x of s. How? Let's go back to the table again. You see here, there is a property called differentiation in S domain. What it says is minus t into x of t will have the Laplace transform d by ds of x of s, or take this negative to other side. Okay, so or t of x of t will have the Laplace transform minus d by ds of x of s. That's what I have used here. Okay, and what is x of s? We know that x of t is equal to u of t. Therefore, x of s will be equal to 1 by s. That means what is this? Minus d by ds of 1 by s, which is equal to 1 by s square. And again, the ROC is real part of s to greater than 0. Okay. Fourth one, e power minus at into u of t. Okay. What is the Laplace transform of e power minus at into u of t if you know the Laplace transform of u of t? Same thing again, use Laplace transform property. If x of t has a Laplace transform x of s, then e power minus at into u of t, sorry, x of t has a Laplace transform x of s minus s naught. Okay, that is basically shifting in the s domain property. So here, let's say x of t is equal to u of t. Therefore, x of s is equal to 1 by s. Implies e power minus at x of t will have the Laplace transform 1 by S plus A, because S naught is equal to minus A. Well, this is S naught T, not E power. Okay, maybe I did a mistake here. This is just S naught T. Okay. And what is the ROC? Real part of S greater than minus A. See, again, this is see how to identify whether, how to cross verify whether it's a correct ROC or not. Look at the signal. It's a right-sided signal, so ROC should be right-sided. So it is a correct ROC. E, cos omega naught T into U of T. Okay. So now let's try to do this. This is nothing. You can write this as half of e power j omega naught T plus e power minus j omega naught T times U of T. Or the same as half of e power j omega naught T into U of T plus half of e power minus j omega naught T into U of T. Okay. So let's say this is the first term. This is the second term. Okay. Let's compute the Laplace transform of the term 1. So again, there's nothing but shifting in S domain property. Why? Because essentially I know the Laplace transform of U of T. I'm asking what is the Laplace transform of e power j omega naught T into U of T. Half, of course, no problem. By linearity, again, half will multiply in X of S also. So by this shifting in S domain property, Laplace transform of half into e power j omega naught T U of T, sorry, X of T, U of T will have the Laplace transform half of, maybe I'll write for general X, then we'll go to U. Okay. We'll have the Laplace X of S minus j omega naught, because j omega naught together plays the role of S naught. Okay. But I know that at X of T, when you use U of T, then X of S is nothing but 1 by S. So this Laplace transform will become half of S replaced by S minus j omega naught. Half of 1 by S minus j omega naught. Similarly, Laplace transform of term 2. You can show that similarly, the only difference is in term 1 you have plus j omega naught, in term 2 you have minus j omega naught. That's the only difference. That is, S naught is now, this term will now become negative of the term in term 1. That is similar. So term 2, the in S naught is equal to minus j omega naught. So your Laplace transform will be equal to half of X of S plus j omega naught, which is nothing but half of 1 by S plus j omega naught. Therefore, your total Laplace transform is Laplace transform of term 1 plus Laplace transform of term 2. Why can I add? Because of linearity. Linearity says that if x1 of t has a Laplace transform x1 of s and x2 of t has a Laplace transform x2 of s, then the Laplace transform of x1 of t plus x2 of t is equal to x1 of s plus x2 of s. So if you essentially compute these Laplace, so what, half of 1 minus s minus j omega naught plus half of 1 by s plus j omega naught. If you basically basically take the conjugate and rationalize the denominators and do all this stuff, you can show that this simplifies to s by s square plus omega naught square, with ROC again being a positive right-sided ROC. That is the Laplace transform of cos omega naught t times U of t. Maybe, okay, we have done so far. I'll give homework of one more. You just try it on your own. Okay, what is this? This is E. F is e power minus at into cos omega naught t into U of t. Just try as a homework. Very, very simple. Just make use of I can tell you the answer right away, but you just try to. So basically, you know, cos omega naught t u of t will have s by s square plus omega naught square. This guy has this as a Laplace transform. It is multiplying another e power minus at. So s will become s plus a. So it will be s plus a divided by s plus a the whole square plus omega naught square, and real part of s greater than minus a. Okay, that's basically the answer. I've told you the final answer, but you can just try to write it little systematically, you know, from first principles and prove it. Okay, this is homework. Okay, I think this is a good time to see if there are any questions. Are there any questions? Is everything clear? At least one of you can unmute and tell. Is it clear? Whatever I did?
Yes, sir. Yes, sir.
Okay, yeah, thank you. Okay, so let's move on to the next question. Question number 2. Let x of t equal to e power minus 3t into u of t minus 2 minus e power 5t into u of 4 minus t. Find x of s. That is what I'm saying is, okay, your time domain signal is this. What is its Laplace transform? That's all. Very straightforward, but let's do it systematically. Answer. The trick is to first separate out different terms and then again use linearity of Laplace transforms. So let me rewrite. X of t is nothing but e power minus 3t into u of t minus 2 minus e power 5t into u of 4 minus t. So what I'm doing, e power minus 6 into e power minus 3 of t minus 2 into u of t minus 2 plus minus e power 5t into u of 4 minus t. See what it did essentially, this minus I took it as plus of minus, and I multiplied and divided, I multiplied e power minus 6 and e power 6 so that this is equal to 1. And I took e power 6 as minus 3 of t minus 2. That's the only thing I did. Now let's do term by term. This is term 1. Term 1. This is term 2. So the Laplace transform of x of t will be Laplace transform of term 1 plus Laplace transform of term 2. Okay. So let's take the Laplace transform of term 1. First term, term 1. We're just going to use the properties of Laplace transform to derive the Laplace transform of term 1. Now, you see, how did we get this first term? You take u of t, and then you do e power minus 3t into u of t, and then you do time shifting. Becomes e power minus 3 times t minus t naught into u of t minus t naught. Okay, maybe one more step. I will write little small. Minus 3t into u of t minus t, and this becomes e power minus 3t 3t minus 2 into u of t minus 2, and then it becomes e power minus 6 into e power minus 3t t minus 2 into u of t minus 2. This is a sequence of operation to get the first term from u of t in the time domain. Now let's write the corresponding Laplace domain. So u of t has the for Laplace transform 1 by s. So if u of t has a Laplace transform 1 by s, what is the Laplace transform of e power minus 3t into u of t? Just use the property. Recall what is go back again. Again, like this, we need to practice problems to remember the properties. If x of t has a Laplace transform x of s, then e power s naught t into x of t will have the Laplace transform x of s minus s naught. That's what we will do here. So here e power minus 3t into u of t will have the Laplace transform 1 by s plus 3. Now what I'm doing? I'm doing time shifting. T replaced by t minus 2. That will cause, and by how much I'm doing? By 2. A factor, I'm doing by a factor of 2. Right? So this will become e power minus 2s by s plus 3. Time domain shifting. If you shift in the time domain, you multiply by exponential in the Laplace domain. And by a factor of 2, you're shifting, so you'll multiply e power 2s. And finally, you're multiplying this by a constant e power minus 6, and that will also get multiplied e power minus 6 into e power minus 2s by s plus 3. So this is the Laplace transform of first term. Is it clear? Anyone confirm? I just use the property of Laplace transform in every step. Is it okay? One of you can confirm if it's okay.
Yes, sir. Yes, sir. Continue.
Yeah. Okay. Similarly, let's compute the Laplace transform of term 2. Okay. What do we have? We have minus e power 5t into u of 4 minus t. Okay. Okay. I will do the following. First of all, I will rewrite term 2 as e power minus 5t into u of 4 minus t. This is same as e power minus e power 20. Okay, there is already a minus here. Okay, if you don't forget the minus. Minus e power 20 into e power okay, there was a plus or minus here. Oh, it's just plus 5t, not minus 5t. So okay, it's a plus 5t. Okay, so e power 5 of t minus 4. All I did is I did e power 20 times e power minus 20. That's what I did here. Into u of 4 minus t. And this is same as minus e power 20 into e power 5 of t minus 4 into u of minus of t minus 4. This is how I've rewritten term 2. Now look at this sequence of operation. Take u of t first, then make it minus e power 5t into u of minus t, and then make it e power t minus 4. This is basically like shifting in S domain. This step is like shifting in S domain. This step is shifting in time domain. Okay, that's by a unit of 4. So this will become t replaced by t minus 4. So t minus 4. And finally multiply e power 20. Okay, minus e power 20 into e power 5t minus 4 into u of minus of t minus 4. This is a sequence of operation to arrive at term 2 in the time domain from u of t. Now we'll do the same, use the properties of Laplace transform and find the Laplace transform of term 2. U of t has a Laplace transform 1 by s. The Laplace transform of minus e power 5t into u of minus t is 1 by s minus 5, except that ROC here will be real part of s is less than 5. Okay, by the way, here for term 1, what is the ROC? See, it's a u of t. So this is a right-sided signal. So ROC should be right-sided. So you can show that the real part of s greater than minus 3 is a ROC for term 1. For term 2, real part of s should be less than 5, because you're talking about Laplace transform of a left-sided signal. So the ROC should also be left-sided. Now do shifting in the time domain. So it's time shifting. So you'll be having a multiplication in the e power exponential multiplication in the Laplace domain by a factor of 4. So it is e power minus 4s by s minus 5. And then e power 20 is multiplied. So you'll get e power 20 into e power minus 4s by s minus 5. What is the ROC is nothing but real part of s is less than 5. Now Laplace transform. So let's just quickly summarize. Laplace transform of first term is nothing but e power minus 6 into e power minus 2s by s plus 3 with ROC, real part of s, greater than minus 3. Laplace transform of second term, e power 20 into e power minus 4s by s minus 5 with ROC, real part of s, less than 5. Therefore, your total x of s is the sum of both the Laplace transform, e power minus 6 into e power minus 2s by s plus 3 plus e power 20 into e power minus 4s by s minus 5. What is the Laplace transform? R1 intersection R2. That is, real part of s is greater. That is, how will the real ROC look like? This is your j omega axis and this is your sigma axis. You mark 5 and you mark 3. And then basically everything in between. This is the ROC of the curve. Now basically go back and look at the time domain signal. U of t minus 2 is a right-sided signal. U of 4 minus t is a left-sided signal. So the entire signal is two-sided signal. That is why your ROC turned out to be a finite strip in the complete S domain. So the Laplace transform is this plus this with ROC given by a real part of S between minus 3 and 5. Okay, so that basically finishes this question. Are there any questions? If there are any questions, you can ask at this point. Otherwise, it is now 7:03. We will take a break for about 15 minutes. So we will continue around 7:18 or maybe okay, 7:20 we will continue. Okay, you can all stay online.
Okay, sir.
7:20 we'll again continue. We'll just take a break until that time.
Okay.
Okay, let's resume. So the next question for today is question number 3. What is the Laplace transform of t into e power minus at into u of minus t? Okay. Now what we will do is we will quickly recollect the properties of Laplace transform. If you have minus e power minus at answer, okay, minus e power minus at into u of minus t will have the Laplace transform 1 by s plus a. So e power minus at into u of minus t will have the Laplace transform minus 1 by s plus a, because it's just linearity, right? So I can just multiply minus 1 on both sides. So let's say this is your x of t. Therefore, t into x of t will have the Laplace transform what? Minus d by ds. So the minus 1 by sa plus is 1 x of s. So minus d by ds of x of s. But t into x of t is nothing but t into e power minus at into u of minus t. And the Laplace transform is minus d by ds into minus 1 by s plus a. And this is nothing but d by ds of 1 by s plus a, or minus 1 by s plus a the whole square. And what is ROC is nothing but real part of s is less than minus a. Why? Because it's a left-sided signal. So it should be a left-sided ROC. Okay? So that's all. So the Laplace transform of t into e power minus at into u of minus t is minus 1 by s plus a the whole square with this as the ROC. Okay, all I did is just first first took u of minus t, and then you took the Laplace transform of e power minus at, and then Laplace transform t into a power minus at. You can do everything using properties of Laplace transform. Question number 4. Find the Laplace transform of y of t equal to t into x of minus t. Okay, in terms of x of s, that is the Laplace transform of x of t. All I'm saying is you just don't find for t into x of t. You do a time reversal to x of t and then multiply with t. What will be the Laplace transform of the resulting y of t in terms of x of s? That is the Laplace transform of x of t. Okay. In fact, this is another interesting thing you can remember. It's a property, not a basic property, but a derived property using the existing properties of Laplace transform. Let's do this. So what is the definition of Laplace transform? X of s is nothing but integral minus infinity to plus infinity x of t e power minus st dt. Now just to avoid confusion, let me denote z of t is equal to x of minus t. What is z of capital Z of s? It's nothing but integral minus infinity to plus infinity x of minus t. I mean z of t is nothing but x of minus t into e power minus st dt. Now what I do, you do a variable substitution, t replaced by minus t. Therefore, what will this happen? Minus infinity will become plus infinity, or if t becomes minus t, then dt will become minus dt. And minus infinity will become plus infinity will become minus infinity, and there'll be a minus outside because of dt become change in sign. And and you'll have x of t into e power, okay, there's a minus here, so this becomes plus st dt. Now you do minus of integral infinity to plus minus infinity, or the same as minus infinity to plus infinity x of t e power st dt. Now this is nothing but x of minus s. Why? If x of s has minus s here, then x of minus s will have a minus of minus s, which becomes x of t into e power st integral dt. That is exactly this. So it is nothing but capital X of minus s. So what does it mean? It means that if x of t has a Laplace transform x of s, then x of minus t will have the Laplace transform x of minus s. Okay, it's a good property to remember. Fine. Now z of t is what? X of minus t. Now define y of t is equal to t into z of t. Therefore, by property of Laplace transform, t into z of t will have the Laplace transform minus d by ds of z of s. But z of s is nothing but x of minus s. Because we know that z of t is x of minus t, whose Laplace transform is x of minus s. So put that here. You get minus d by ds of x of minus s. That's all. Therefore, t into x of minus t will have the Laplace transform minus d by ds of x of minus s. Okay. So just I manipulated the existing properties of Laplace transform and I found the answer. Okay. Next question. Find the inverse Laplace transform of x of s equal to 8s squared plus 11s by s plus 2 into s plus 1 whole cube, and the ROC real part of s is greater than minus 1. But what does it mean? This says that ROC is right-sided, which means your signal should also, time domain signal should also be right-sided. That's the hint. Okay. Means you have to find the x of t for which x of s is given by this value with ROC this. That is the meaning of inverse Laplace transform. And if you remember today in the summary, we told that partial fractions are very helpful to find the inverse Laplace transform. And we will essentially take that approach only today for solving this question. Okay. So answer. First of all, we need to find the poles of the x of s. So what are the poles of x of s? Wherever the denominator goes 0 and they occur at s equal to minus 2, which is a distinct simple pole because it occurs, the factor is only one simple distinct pole, and it s equal to minus 1, which is a repeating pole 3 times. Repeating poles and 3 times it repeats. Therefore, by partial fractions, partial fraction expansion, what we have, we can write x of s as some k1 by s plus 2. This is the partial fraction for s equal to minus 2 pole, and 3 more terms representing the partial fractions for the repeating term, repeating pole of s equal to minus 1, plus k2 by s plus 1 whole cube, plus k3 by s plus 1 whole square, plus k4 by s plus 1. We call this equation 1. Right? Why did I write 3 terms? Because it is repeating 3 times, so I will have all the order from 1 to 3. Okay, now what remains to be found is what are the values of k1, k2, k3, k4. We'll find that first. Value of k1 is simple because it's simple pole. K1 is nothing but x of s into s plus 2 at s is equal to minus 2. Let's just do that. What happens is x of s is nothing but x of s into s plus 2 will become k1 plus k2 by s plus 1 whole cube into s plus 2 plus k3 by s plus 1 whole cube into whole square into s plus 2 plus k4 by s plus 1 into s plus 2. Now at s equal to minus 2, what will happen? This will go to 0. This will also go to 0. This will also go to 0 because s plus 2 will become 0. But k1 will only remain equal to k1. Okay? That is why it's equal to k1. So what is this? So k1 is equal to x of s into s plus 2 at s equal to minus 2. Now what is x of s? This guy. 8s square plus 11s by s plus 2 into s plus 1 whole cube. We'll just do that. 8s square plus 11s by s plus 1 whole cube into s plus 2 into s plus 2 at s equal to minus 2. S plus 2 get cancelled. At s equal to minus 2, this comes out to be minus 10. Now k2. K2 is nothing but is a coefficient of 1 by s plus 1 whole cube. So this, as per the expression, k2 equal to x of s into s plus 1 whole cube at s equal to minus 1. That is 8s square plus 11s by s plus 1 whole cube into s plus 1 s plus 2 into s plus 1 cube. So this and this get cancelled. At s equal to minus 1, this turns out to be minus 3. Now k3, you can show that k3 is equal to d by ds 1 by 1 factorial d by ds of x of s into s plus 1 whole cube at s equal to minus 1. That is nothing but d by ds of 8s square plus 11s by s plus 2 at s equal to minus 1. Let's just do this. This becomes s plus 2 is like that, s plus 2 into 16s plus 11 minus 8s square plus 11s into 1 by s plus 2 the whole square at s equal to minus 1. Now if you just put s equal to minus 1, this will turn out to be minus 2. Finally, k4 equal to 1 by 2 factorial into d square by ds square of x of s into s plus 1 whole cube, and finally at s is equal to minus 1. You can verify that this value comes out to be 10. Therefore, your x of s is equal to minus 10 by s plus 2 minus 3 by s plus 1 whole cube minus 2 by s plus 1 square and plus 10 by s plus 1. Okay, and now you see, so you have been able to find x of s as separable terms. Now what we'll do, we'll find the inverse Fourier Laplace transform of each of these terms separately. So now you see, what is the inverse Laplace transform of minus 10 by s plus 2? Minus 10 into e power minus 2t into u of t. How did I say it is only u of t, not u of minus t? Because I know that ROC is right-sided, given in the question. That's why I wrote it as u of t, not minus e power minus 2t into u of minus t. No, because that is left-sided signal. A right-side ROC means the signal should be right-sided. That's why I wrote this as the inverse Laplace transform. Now this one not quite straightforward. We will derive it. Okay, this one let's call it as term 2. Similarly, let's call this as term 3. And what is the Laplace transform? 10 by s plus 1, 10 into e power minus t into u of t. Now let's do the inverse Laplace transform of term 2, ILT of term 2. Okay, L inverse, I'm just denoting L inverse of 1 by s plus 1 whole cube using the properties. You see, this here we have this. Let me go back all the way to the table that I display here. You see here, this is like the ROC is right-sided and 1 by s plus alpha power n. We have n is equal to 3. So t power 2 by 2 factorial into e power minus alpha t. Here alpha is equal to 1 for us, so it's e power minus t into u of t. So this is the inverse Laplace transform of, term 2. Equal to 1 by 2 factorial into e t square into e power minus t into u of t. Similarly, inverse Laplace transform of term 3. L inverse of 1 by s plus 1 whole square. In fact, you have 3, right? 3 into, because term 2 contains a 3 also, so it is basically 3 by 2 factorial. Okay. Similarly, inverse Laplace transform of 2 into inverse Laplace transform of 1 by s plus 1 whole square turns out to be 2 times t into e power minus t into u of t. Therefore, what we'll do, we'll just add all of them. Therefore, x of s, small x of t equal to 10, that is from here, and you have there is a minus in front of 3 and second term, so minus 2t minus 1.5 t square. 2 factorial is 2, so 3 by 2 is 1.5 t square, and minus 10 times e power minus 2t whole times u of t. That's all. So 10 times minus 2t minus 1.5 t square whole times e power minus t minus 10 times e power minus 2t whole into u of t. This is the inverse Laplace transform, or in other words, this is a signal x of t for which the Laplace transform is this number with ROC is this. Is this clear? Can anyone confirm if this is clear? Yes? Can anyone unmute and say if it's clear? Hello? Can you confirm?
Yes, sir.
Okay. Okay. Now next, let's do the next question, which is question number 6. This is question number 5, right? Yeah. Question number 6. Find the inverse Laplace transform of x of s equal to 4 by s plus 2 into s plus 4 if ROC is A, real part of s lying between minus 4 and minus 2, B, real part of s is less than minus 4, C, real part of s is greater than minus 2. So these are 3 different ROCs, and in each of these possibilities, you should find the inverse Laplace transform. For example, this is a finite width, right? Between minus 2 and 4 is where the ROC lies. And real part of s less than minus 4 means it's a left-handed ROC. This is minus 4. And real part of s greater than minus 2 means let's say this is minus 2, then this is a right-handed ROC. Okay? Answer. First step is again to represent the given Laplace transform in partial fraction expansion. So poles of x of s occurs at s is equal to minus 2 and minus 4. Both are simple distinct poles because it occurs only once. And with the factor exponent is 1. It doesn't come as x plus 2 whole square, just x plus 2. Distinct poles. And so basically, therefore, by partial fraction expansion, You can write x of s is equal to k1 by s plus 2 plus k2 by s plus 4. Where what is k1? K1 equal to x of s into s plus 2 at s equal to minus 2. But what is x of s? X of s is given to be 4 by s plus 2 into s plus 4. 4 by s plus 2 into s plus 4 into s plus 2 at s equal to minus 2. So this and this will get cancelled. At s equal to minus 2, this comes out to be 2. Similarly, k2 equals x of s into s plus 4 at s equal to minus 4. It's nothing but 4 by s plus 2 into s plus 4 into s plus 4 at s equal to minus 4. So s plus 4 at 4 get cancelled. So it is 4 by minus 2 equal to minus 2. Therefore, x of s equal to 2 by s plus 2 minus 2 by s plus 4. Now case 1. What is given? ROC is such that real part of s between minus 2 and minus 4. So basically, first term, this is basically term 1. Term 1. And this is like term 2. I'm including minus in term 2. That means it's basically 1 plus 2. Okay? It's basically x of s. So term 1. So inverse Laplace transform of term 1 of 1. What do we have? 2 by s plus 2. And ROC for this term is a real part of s is greater than less than minus 2. So as far as this Laplace transform is concerned, it's a left-handed ROC. Therefore, inverse Laplace transform is ILT equal to minus 2 times e power minus 2t into u of minus t. Now, okay, because it's a left-hand ROC, so the inverse Laplace transform will also be left-handed. If it were right-handed, then it will be plus 2 times e power minus 2t into u of plus t. Okay, go back and see here. This table, yeah, this is table. E power minus alpha t into u of t will also have s 1 by s plus alpha. Minus e power minus alpha t into u of minus t will also have 1 by s plus alpha. The only difference is ROC. If it's a right-sided ROC, then it is right-sided signal u of t. If it's a left-sided ROC, then signal is also left-sided. Based on this only, I wrote left-sided signal. Okay. So now ILT of term 2. Minus 2 by s plus 4. And for this term, real part of s is greater than minus 4. Therefore, it's a right-sided ROC, a right-handed ROC. Therefore, ILT equal to minus 2 times e power minus 4t into u of t. Note that this minus is coming because of this minus. But this minus is coming because of being left-handed ROC. Okay. So then what do? We just club both. This is let's say A and this is B. Adding A and B, the inverse Laplace transform is minus 2 times e power minus 2t into u of minus t minus 2 times e power minus 4t into u of t. So clearly you see here, this is a left-sided signal, this is a right-sided signal. So this is a both together, it's a two-sided signal. That is why the ROC is a finite strip. Okay, now let's move to the second case, B case, where the ROC is such that our real part of s is less than minus 4. B. Real part of s is less than minus 4. What does it mean? So you have sigma and j omega and you have -4 here, -2 here, and ROC is here. That means, what does it mean? If real part of s is less than -4, automatically real part of s is less than -2 also. Okay, because -2 is greater than -4. So if real part of s is less than -4, real part of s is also -2. That means both are left-handed ROC. Okay, therefore, inverse Laplace transform of term 1. Term 1 is what? 2 by s plus 2. 2 by s plus 2 with a left-handed ROC, it becomes -2 times e power -2t into u of minus t. This is same as the previous, because here also we had left-handed ROC. But now here, in the previous case, we had right-handed ROC, but now that also became left-handed ROC. So I'll inverse Laplace transform second term is -2 by s plus 4, and its inverse Laplace transform, because of being left-handed ROC, it is minus of this minus because of this minus -2 times e power -4t into u of minus t, or which is equal to 2 times e power -4t into u of minus t. So again, call this as c and d and add both c and d. Adding c and d, we get x of t equal to 2 times e power -4t minus e power -2t into u of minus t. So you see, this is left-handed signal. This is left-sided signal, because this is also u of minus t, this is also u of minus t. So sum of, or any difference of sum of two left-handed signals is again a left-handed signal. That's why your ROC is also left-handed. Okay, and final case C is when real part of S is greater than -2. So you see, what does it mean? You have a sigma axis, you have j omega, and this is -2 is here and -4 is here, and this is the ROC. If real part of S is greater than -2, automatically real part of S is also greater than -4 also, because 4 is before -2. So real part of S is also greater than -4. That means the ROC for both the terms is right-sided. So ILT of term 1. What is term 1? 2 by S plus 2. 2 by s plus 2 will have the inverse Laplace transform 2 into e power -2t into u of t. And similarly, call this as e. And similarly, inverse Laplace transform of term 2, which is -2 by s plus 4, which is nothing but, whose inverse Laplace transform with right-sided ROC is -2 times e power -4t into u of t. This is called equation F. Adding E and F, x of t is equal to 2 into e power -2t minus e power -4t into u of t. This is a right-sided signal, because this is, first term is also e power -tt into u of t, which is right-sided. Second term is e power -4t into u of t, that is also right-sided. And if you do sum or difference of any two right-sided, that is also going to be right-sided. So that's why it's a right-sided signal. This also, see, that this because your ROC was right-sided. Okay, so this says that your ROC is very important. See, in entire problem, your x of s was same, but depending on the ROC, the actual time domain signal could be either this number, or could be this signal, or could be this signal. All three are different signals. Okay, so ROC is very important if you want to uniquely tell what is the signal transform pair. Otherwise, you cannot uniquely tell. Okay, let's do one more question related to this and let's stop with that. Okay, similar to this only. This is question number 7. Consider a continuous time LTI system for which the input x of t and output y of t are related by d square y of t by dt square plus dy of t by dt minus 2y of t equal to x of t. There's nothing but a linear constant coefficient differential equation. The input and output of an LTI system are related by this differential equation. Question A. Find the transfer function h of s. Number 2. B. Determine the impulse response h of t for the following 3 cases. First case is system is causal. B is 2. System is stable. 3. System is neither causal nor stable. Okay. Actually, it's very good, very simple question. All you need to do is you need to use the properties of these systems. That is, if the system is causal, how will the ROC look like? System is stable, how will the ROC look like? The system is neither causal nor stable, how will the ROC look like? So for these 3 different cases of ROC, find the inverse Laplace transform derived in part A. That's all is the question. That's basically the way you need to solve the question. First is to find h of s, the transfer function. Part A answer. So what you do is you define this differential equation as equation 1 and this is equation 1 and take Laplace transform on both sides to equation 1. A part, take Laplace transforms to equation 1 on both sides. Okay, so basically you're by using the properties of Laplace transform, if you differentiate y of t 2 times, then the Laplace transform of that term will become s square times y of s plus one time differentiation means you multiply 1s times y of s minus 2y of s equal to x of s. That's all. Now just rearrange. Means s square plus s minus 2 into y of s equal to x of s. Or your transfer function is nothing but h of s is equal to y of s by x of s, right? That's the definition of transfer function, equal to 1 by s square minus plus s minus 2. This you can factorize it as 1 by s plus 2 into s minus 1. Okay, therefore this is the required transfer function. Now going to B part. We need to find the impulse response. What is the impulse response given a transfer function? It's an inverse Laplace transform. But for that, you need to have ROC. That's why these 3 cases are given. Okay. Within B, we'll do partial fraction expansion and make the transfer function little simplified. By partial fraction expansion, You can write h of s as k1 by s plus 2 plus k2 by s minus 1, where k1 equal to h of s into s plus 2 at s equal to minus 2. You can show that this will come out to be minus 1 by 3, and k2 equal to h of s into s minus 1 by at s equal to 1, and this will come out to be 1 plus 1 by 3. Therefore, your transfer function can be further simplified as minus 1 by 3 into 1 by s plus 2 plus 1 by 3 into 1 by s minus 1. This is the transfer function, a simplified version of transfer function. Now, let's talk about the impulse response if system is stable. Causal. First is what? They're asking what is the impulse response if the system has to be causal. System is causal. What does it mean? Your ROC should be right-sided. ROC should be right-sided. That is the property of a causal system. The ROC of the transfer function should be right-sided if the system has to be causal. So now you see also what we know is what are the poles? Poles are nothing but -2 and 1. But I know that ROC does not contain pole. Therefore, the right-handed ROC is nothing but real part of S greater than max of -2 and 1, which is equal to 1. Therefore, if real part of S is greater than 1, automatically that is also greater than -2. So both are right-handed ROC. Therefore, now it's simple. All you need to do is invert this Laplace transform, inverse this Laplace transform for right-handed ROC. If you do that, what you will get is x of t will be equal to, h of t. This is not x of t because impulse response h of t equal to -1 by 3 into e power minus 2t into u of t plus 1 by 3 into e power minus t into u of t. So this is the impulse response of the system which satisfies, which basically is governed by this is the system which is governed by this differential equation will be causal if the impulse response is this given by this expression. Okay. Similarly, now the next thing is what? I want the system to be stable. System to be stable. Now, in terms of ROC, what does stability mean? Implies ROC should contain j omega axis. That is, if I have, let's say, sigma axis and j omega, your ROC should be containing j omega. That is, both the left and right side of j omega, ROC should be present. Means what? The only possibility in the for this to happen is, see, this is basically -2 and this is basically 1, because see, there are two poles for this, -2 and 1. There are the two poles, and -2 and 1 are here. ROC should not contain poles. That means the only possibility for the system ROC to contain j omega axis is when ROC is such that real part of S is greater than -2 but less than 1. This is the only possibility in which the ROC will contain j omega axis. Therefore, you can show that inverse Laplace transform, just do it out like the previous question. It comes out to be -1 by 3 e power minus 2t u of t -1 by 3 e power t into u of minus t. That is basically, it is both right-sided and left-sided or two-sided signal for which the ROC is a finite state. Finally, system is neither causal nor stable. That means what? It should not be causal. It should not be stable. No stability. Sorry, no stability means ROC should not include j omega axis. And no causality means ROC should also be left-sided. It can be right-sided, but it should also contain left-sided also. Only then it will not be causal. It will also be left-sided. Based on this, you can show that the only possibility for ROC is real part of S is less than -2. This is the only possibility. Okay, ROC should be left-sided actually. Okay, this is the only possibility. Because this implies that ROC, real part of S, is also less than 1. Both so just this is enough. Now using these two, you can invert the Laplace transform of both the terms and show that your h of t equal to 1/3 into e power -2t into u of minus t minus 1/3 into e power t into u of minus t. So it is a left-sided signal. Because for left-sided signal, left-sided impulse response, it is not stable because it doesn't contain j omega axis, and it cannot be causal because it is left-sided. It's not right-sided. Okay. So depending on what is the requirement for the system, you can have different impulse response, and basically that is governed by the region of convergence ROC. Okay, so we'll stop here. If there are any questions, I can answer now. Otherwise, we'll continue in the next week. Are there any questions? Okay, so I see that which books would you recommend for the subject? Okay, so I think the good books you should refer is Oppenheim. Author is Oppenheim, and the Signals and Systems is the title of the book. The other book I would recommend is Signals and Systems by Simon Higgins. Both these books are good enough.
Thank you, sir.
Yeah. Okay. Then let's stop for today. Thank you all.